Hey folks, Mrs. White here, coming at you again online, not in person. This is so fun. Anyways, we are finishing up our work on Chapter 11. We're looking at Section 4 today, which has us looking at two samples, just like everything else in this chapter, and specifically looking at two samples and how we can compare their standard deviations. And remember, standard deviations has us look at kind of like the spread of our data, right? A smaller standard deviation would mean it's clustered around the average. A larger standard deviation would mean that it's more spread out. And so that's what we're going to be doing today. If you remember back to chapter 10, we ended up learning about the chi-squared distribution, and how it wasn't really symmetrical. Well, chi-squared is not used with two samples. It's going to be something different called the F distribution. And so we'll talk about the F distribution today, some of the notation that kind of goes with that. We'll talk about how we can use that to find critical values if we're doing the classical method, and then how to do hypothesis testing with it. So your note-taking guide for today has examples specifically around finding critical values because it's tricky. And then hypothesis testing, there's two examples of that this time around. So you can find that attached to the video. You'll also find the homework assignment. It is only 2 problems, which is kind of nice. Take your time, do your best, and if you have any questions on 11.4, feel free to show up to office hours on Friday. I'd be happy to go over those 2 problems or any other topics covered in this video. There is one of the questions on your Chapter 11 quiz that covers standard deviation, so you do want to make sure that you have an idea of what the heck you're doing with it. My plan for Monday is to do a work day / go over homework problems day. So depending on feedback that I get from you folks and or my office hours on Friday, I will probably just post the keys to the homework and then hold office hours on Monday during 1 to 2 just to see if anyone has questions they want to pop on and ask. That's my tentative plan for Monday. When we get together next Thursday, we're going to be reviewing for our Chapter 11 test, which you'll be taking the following week at home. And by the following week, I mean the following week is April break. So if you end up wanting to take it right after we do the review, you're welcome to, as long as you can set that up with your parent. If you want to wait till after April vacation is done and do it that following Monday, you're welcome to do that also. I won't be providing any additional review though. So if you're planning on staying home, you're more than welcome to take that test before April vacation. But I won't be posting anything new over April break, and I will give you Monday, Tuesday, Wednesday to finish that up. It just has to be posted by the Wednesday after April break so that I can grade it. If you haven't checked out my expectations, I would encourage you to. Most people have at this point, but one of the things on that is that we're not going to have one big, large test at the end. We're going to have a Chapter 11 test and a Chapter 12 test. And then what I'll do is I'll average those 2 grades, and that will be your test 4 grade. I'm doing this because it's easier that way for you folks to kind of departmentalize each chapter. It also was, we've been granted permission through UMA to do that, and all the other stats teachers that do dual enrollment are doing the same thing. So we're pretty fortunate we're so far into the curriculum that all we have is Chapter 11 and Chapter 12 left, and Chapter 12 is going to be nice and quick just like this one was. So if you have any questions about that, feel free to also stop in during office hours and ask, or send an email. That's fine too. Okay? So let's start off by doing a problem. It's going to be covering 2 samples, but we don't know what calculation to do. Okay, so it's from Chapter 11, but we do not know which keystroke to use or what they're asking. So let's read it and try to pick out the pieces and parts that are important. So John has an online company that sells custom rims for cars and designed 2 different web pages that he wants to use to sell the rims online. However, he cannot decide which page to go with, so he decides to collect data to see which site results in a higher proportion of sales. He hires a firm that has the ability to randomly assign one of his 2 web page designs to potential customers. With web page design, John secures a sale from 54 out of, with web design 1, John secures a sale from 54 out of 523 hits on the page. With the second design, he secures 62 out of 512 hits to the page. So first things first, there's two samples because there's two different web pages. Wow, this pen needs, I think, a new battery. It's not working great. So he has two samples. Then we need to determine, are we comparing proportions? Are we comparing dependent means? Are we comparing independent means? And then after today, are we going to be comparing standard deviations? So there's two ways you can make that assumption. Hopefully right now you're saying that they're proportions because the word proportion is literally right here. But if they give you raw data like something out of something else and something out of something else again, that's a pretty strong indicator that you're dealing with proportions. Okay, so this is going to be stuff from section 11.1. So the first question is, what is the response variable in this study? What is the explanatory variable? So what are the variables that we're measuring? Well, the response is your outcome, okay? So your outcome is the amount of sales, okay, that we're looking at. So the amount of sales. The web page design, okay, is going to be the explanatory variable. That's the reason behind those sales occurring, okay? So the web page design comes first. The response variable, or whether or not they buy something, comes second, okay? Next, based on these results, which page, if any, should John go with? Why? So this is actually how people do testing to see whether or not they're going to do web page designs. I mean, your text is saying that Target does it. That's a pretty big company. So in order to be able to make this decision on whether it actually matters or not, we should do hypothesis testing of two samples that are both proportions. So to start off, we should or would check for normality. They do say that it's random. Okay, we don't have to worry about independent or dependent because we have a proportion. Okay, we do have to make sure that our sample size is less than 5%. So clearly people that are using the internet, this is definitely less than 5%. And so we can make some assumptions about it being normally distributed. So now we're ready to write our null and our alternative hypothesis. Now, with proportions, you can set them up as two separate instances. So we'll do this as our P1, and we'll do our second page design as P2. Okay? So our null is that it doesn't matter which page design you do, so that the amount of people that say yes for page 1 and the amount of people that say yes for page 2 are going to be exactly the same, okay, the amount of people who actually do purchase. Because, let's see, based on these results, which page, if any, should John go with? So now we have to make an assumption. One of them is going to be greater than the other, right? One is going to receive more sales than the other one. Now in our calculator, we have P2 as always set up on this side, but if we decide that P2 should be greater, then we can just flip-flop our symbol. So to make the decision about which one should go where, you might want to just put this one first and this one second, but we should figure out what our P hats are for both of these. Okay, that way we know if that one is actually significantly larger or not. We don't want to do different here because if we're choosing, yes, we should go with it or go with the other one, then we can't have not equals. Okay, that would just mean you would choose one or the other. So I'm going to set up my P hat. I'm going to do 54 divided by 523. And I'm going to get 0.1032, so about 10%. Now I'm going to do my P2's P hat. So I'm just going to do 62 divided by 512. And I get that that's around 12%. So I think it's safe to say that this one is what we're testing. Is it actually statistically significantly bigger? So instead of saying greater than here, because I know our calculator has P2 listed when we do our testing in it, we would say, our alternative is going to be that P1 is less sales than P2 actually is, okay? And that it's a big enough difference that it's statistically significant, and our null is that they're exactly the same. If that's tricky to you folks, I can try to explain it again during office hours, but you'll see when we get to the calculator. I'll make sure to point it out to you. So I'm going to test these using, this is my X1, this is my N1, this is my X2, this is my N2. So we're going to go over to our graphing calculator now. We'll clear it out. We're going to go into stat. We're going to go over to tests. And then because we're dealing with a proportion, we are going to go to the 2 prop z test. 2 because there's 2 samples, prop because we're dealing with proportions, and z test because we're dealing with a z-score when we deal with proportions. So down to option 6. My x1 is going to be 54. My n1 is going to be 523. My x2 is going to be, I think it's 62. And my n2 is going to be 512. Now, this is why I said we had to write our alternative a very specific way, right? I wanted P2 to be listed second because here in the calculator, see that, folks? P2 is always listed second. So I want my P2 to actually be larger than my P1. So I'm going to go down and then over, make sure that is chosen. And then now I'm ready to calculate. Now, I'm not going to go traditional on this one. I'm just going to go straight up p-value. So I have 0.18 as my p-value. So my p-val equals 0.18. So right now you're probably like, okay, you said we had to hypothesis test, that we came up with our null and our alternative, and we plugged in all of our stuff. We got a p-value, but we have no alpha to compare it to. Okay, and you had a problem like this on your last test. You had a couple ones, and you kind of had to make some assumptions. So this is 0.18. Alpha values are often 0.01, 0.05, or 0.10, right? We wouldn't hypothesis test anything with because remember, level of significance, our alpha is the probability of making an error. We don't want our probability of making an error to be much higher than this. So even though we aren't given an alpha value here, the fact that this is larger than all 3 of our normal calculations is a pretty strong no. We are not going to reject the null. There's not enough information to say that these 2 are different. 2 sales, when we're looking at that many, is not enough of a difference for it to be statistically significant. So we would actually keep the null because this isn't less than any of our standard alpha values. Okay, so I know that seemed weird because they didn't give us one, but hopefully it makes some sense to you right now that we've talked about it a little bit. All right, so let's get talking about 11.4. Here we're looking again at 2 different samples from 2 different populations, and we're going to be comparing their standard deviations, okay? And like I said before, standard deviations has to do with consistency. So it might be used if we're looking at like stocks. The stock market obviously would look a lot at variance. We want to see how much things change over time. And that would really be where we would use standard deviation, how consistent it is. It could also be when you look at how long a medicine takes to work, you could look at the standard deviation amount of days, and that will let you know out of your samples, how close to that mean it actually is or was, and be able to make comparisons that way. If you remember back to chapter 10, when we looked at the hypothesis test for standard deviations, we learned about chi-squared. And a lot of you maybe don't remember that great because it wasn't on the test and I told you to kind of take a breath. But standard deviations, again, is on this quiz, so it's important that we do take a second to look at it. And there's potential for you to see it on your chapter 11 test also, okay? We are not going to use chi-squared today. Chi-squared only works if you are dealing with a single sample from a single proportion or population, excuse me. Instead, we're going to be using the F distribution, which we'll see momentarily. It's very similar. Before we get going with that, I do want to talk a little bit about the notation. I kind of skimmed over this in the last section, 11.3. We saw some funky stuff, but I want to make sure we're really clear here. So this symbol right here, as far as we've worked with, is population standard deviation, okay? But the step before you actually get your standard deviation for a population is you would square root, okay? Now that step before is also what we would normally have called variance. The symbol for that really is just what we would normally have for our standard deviation squared. Okay, so this symbol, just these 2 pieces right here, mean variance, and then the sub 1 again means that it's coming from that first population. And variance, excuse me, I don't even know where I was going with that. So then the S is sample, okay? And normally we would say it's sample standard deviation, but once you add the squared to it, it's meaning that, oh, we need the sample variance, okay? The sample variance. And then again, the sub 1 means population 1, and this isn't anything new. That's just our sample size of our population 1. So when you see this, they're referring to variance of the population, because of the symbol, from the first sample. Here we have variance from the population of the second sample, or of the second population. The sample variance, okay, from our second population, then our second sample size. So this squared and squared, really, that's just telling the squared means that it's variance, either from our population or from our sample, and then the second two delineates which population is it from. So let's take a look at some of the calculations we're going to do. Let's talk about the actual F distribution. So if we're looking at two different populations, okay, and that's what the 1 means and the 2. So two different population and then variances. So if we're looking at the two variances from two different populations and they're equal, then our sample variances from each of those are going to be independent, simple, and they're going to have their own sample sizes potentially. And then we could come up with this test statistic, which is actually our F value. Instead of getting a T value or a Z score, we end up getting an F value here for our F distribution. And you find that by taking your sample variance from your first and your sample variance from your second population and dividing those two. So it's really important that you list which one's first and which one's second, because we know that the order of division matters, okay? So part of this also is not just getting your F score, okay, which your calculator will do for you, so we're not going to stress out about having that written down, okay, but understanding what it is just a ratio of variances. You do need to be able to identify your degrees of freedom for the numerator and your degrees of freedom for the denominator, okay? Because those are going to be part of how we find our critical value moving forward when we're dealing with our F distribution, okay? So here, this is our test statistic, our F score, and it's just a proportion between our two variances. So the F distribution itself, if you kind of look at it, it changes depending on what your two degrees of freedoms are, okay? Your numerator is delineated with the N, and the D is the denominator. So it's really kind of like from your first population and your second population, okay? But it's the relationship between the two is what's really important, and that's why this is different than chi-squared. If you look at it, you might be like, oh, Miss White, this looks exactly like chi-squared. It starts out really high, and then eventually it will kind of get normal. It starts shifting. Totally right, totally get it. But this graph actually is different because it's taking into consideration the degrees of freedom for both the numerator and the denominator, okay? So we can see that as these increase, the shape changes. This graph generally is not normally distributed, okay? It is going to be skewed to the right, just like our chi-squared distribution, okay? The shape of it, again, is influenced by the degrees of freedom in both the numerator and the denominator. This is a lot like chi-squared, okay, where the shape depended on one degree of freedom, but now it's kind of dependent on the two. Just like any probability curve that we have, whether it's the chi-squared, whether it's the t distribution, whether it's just the normal curve, the area under the curve is always 1. It would represent 100%. And the values of F are always greater than or equal to 0, just like chi-squared, right? If we're drawing a quick sketch of this, we're not just going to draw something that's skewed to the right. We're going to draw the positive quadrant and put it right in there. That way you remember, oh, we can't have negative values here, which does kind of complicate things as we start thinking about critical values. So if you are dealing with something that is right-tailed, so we'll kind of give a little sketch, skewed to the right, okay? Right-tailed would be this proportion here. There's a notation we're going to use for that, okay? So if it's right-tailed, you're usually going to be given a alpha value, right? You're going to have to look at your degrees of freedom in the numerator, the degrees of freedom in the denominator, okay? So if it's right-tailed, we're going to write this location kind of as an F score of 0.05. Because remember, whenever we write something as a sub down here with an actual decimal value, that's area to the right. So the area to the right is going to be 0.05 of our F score. Then we put our degrees of freedom of the numerator and then the degrees of freedom of the denominator listed after it. So if we're looking at this specific one, it says that it's right-tailed, okay? So I'm going to have my F-score of 0.05 because that's what's going to be shaded in over here. The degrees of freedom in the numerator is 10, which means that the sample size was 11. The degrees of freedom in the denominator is 7, which means the sample size for the denominator was 8. Now I'm going to use a specific table in the back of the book and use that information to help me figure it out, okay? If I'm dealing with something left-tailed, and this is where it's even a little funkier, it looks like this, and it would maybe be just this little section right here. I'm still going to use the F, okay, but I'm going to do 1 minus my alpha. And you might be like, Mrs. White, that's not that weird. But you'll see when we look at the table that this usually, potentially, does not exist. And then we're going to do our degrees of freedom in the numerator and the denominator also. Okay? We don't have an example of that here. Now, I want you in your notes to also have that this number, this value, is going to be the exact same thing as 1 over, okay, the F of the original alpha. Okay, so we'll put alpha. We won't put 0.05 there. Okay. 1 over the original alpha, but instead of having your numerator as your first one and your denominator as your second one, you're going to flip-flop those two numbers. So we'll treat our denominator like our numerator and our numerator like our denominator. And you'll see this in an example that we'll do because we're going to do a couple hypothesis testing anyways. So if you are able to do this calculation for the left-tailed, great, awesome. If you cannot because this information isn't available on the table, then you have to do this, where you pretty much find this and do 1 divided by that number. If you're doing a two-tailed test, which is what we're doing in part B here, you have to do both of these. Okay, so you do this for the right tail, you do this for the left tail. The only difference is that you have to take your alpha and divide it by 2, obviously, because your area is cut in half. So we'll take a second. This is actually the first example on your note sheet. So make sure if you haven't printed that out, you're welcome to do so. And then you'll have access to it as we're talking about it. So let's start by sketching out our part A. So we'll do that maybe over here. We're going to do a right-tailed test. So it's going to be here and over. Okay. I'm going to start by writing my correct notation. So I need to find the F-score of 0.05. My degrees of freedom, again, for my numerator comes first, top to bottom, is going to be 10 and then 7. They told me that. Now, here's where you need to write this down, fold the page down in the back of your book, make it very apparent. You're going to go in your book to table, what's it? I think it's 9. But if you go to the foldable insert, you're going to spend forever trying to find it because it doesn't exist in your insert. Okay, you're going to go to the back of your book. It's these pages that have kind of like a blue or a teal next to them. And you're going to go to page A16, and the table continues on to A19. So you're going to go to page A16 through page A19, if that makes sense. Okay, so take a second, pause the video, find that in the back of your book. Maybe stick a Post-it there, fold the corner down because you're going to be using it a lot in this chapter. Okay? So let's do that. Let's go to that page or that span of pages. I'll go to it too right with you right now. Right in the back. So I'm finding my F distribution score. So you can see at the top of all these tables on the next few pages, it says F distribution critical values. So we know we're doing our critical values. If you look to the left-hand side, it says degrees of freedom in the denominator. Across the top, it says degrees of freedom in the numerator. And then it says area in the right tail. So we're doing a right-tailed test, which is good. What you're going to do is you're going to take a look. Our degrees of freedom in the numerator was 10, right? That's that first number we have. So I'm going to go all the way over. I'm actually going to go to page, right now I'm looking at page A17, and I can see the second column going down there is 10. Okay, now I need to, on the left-hand side where it says degrees of freedom in the denominator, I need to find 7, and 7 is on this page, so we should all be on page A17. So if you kind of match those two up, it's in like a little brown rectangle. It says 2.7, 3.64, 4.76, and 6.62, and 14.08. Each of those corresponds to a specific area in the right tail, kind of listed towards the left-hand margin. Okay, so if we look there, we have 0.100, which is the same as having an alpha of 10. Then right underneath that, it says 0.050. And that is what we're looking at here, right? Because they're telling us, oh, we need to do an F of 0.05. So I'm going to go 10 degrees in my numerator, 7 degrees in my denominator, and then I'm going to look over to where 0.050 is. It is 3.68. So my critical value here is going to be 3.68. Ooh, that's not working good. Okay, 3.68 is the critical value that corresponds to that. So if we were to get a test statistic, which is going to be our F score, and it's 4, it's in the shaded region, we would say there is enough evidence, okay? If we had a F score of 2, it would be over here, right, in our not shaded area, so we would say there is not enough evidence to reject the null. We would instead accept it, okay? So that's what that critical value is used for. That's why it's important to be able to calculate it. The more you do it, the better you get. I get that it's kind of tricky. Let's look at our next one, and this is as tricky as they're pretty much going to get because it's two-tailed. So I'm going to start by drawing a picture. I'm going to start with my positive quadrant. I'm going to draw something that is skewed to the right a little bit. I have an area here, and I have an area here, okay? So if my total area that's shaded is 0.05, that means my area here is actually only 2.5% or 0.025, and this area is 0.025. Okay, so if I'm thinking of what is my label for my F score for this one, okay, and this is my left tail, not my right tail. The right tail is what's in the book. It's easier. I could write it as F of 1 minus this area. Okay, so 1 minus 0.025, comma, degrees of freedom in the numerator, 15, degrees of freedom in the denominator, 20. Okay, so I could cross that little expression off right there, right? 1 minus 0.025 is really going to be 0.975. Okay, 0.975. If you go to your book right now, so I could make you do it. I could make you find that 15 across the top, which is on that same page. But then to find 20 across the left, I'm actually going to have to go further in the book. Okay, you would see that 0.975 is not one of the options ever. Okay, and that is going to happen very often. So instead of doing this calculation, I should do 1 over the F of my, again, I'm not going up to this original alpha because it's two-tailed. I'm going back to this specific area here. So I'm going to do F of 0.025. And then I flip-flop my degrees of freedom, okay? I'm going to treat my numerator, which was 15, as 20 now. And my denominator, which was 20, as 15. So when I find whatever score I'm looking for, I'm doing this like it's my numerator and this like it's my denominator, even though in my original problem they're the opposite. So let's find that now, okay? I'm going to do 1 over, I'm going to go to my book, I'm going to go to my page A16 through A19, and I'm going to see what I can do. So in the book, over 2, I'm looking for 20 degrees across the top, 15 across the left. So if I look 20 degrees across the top, is going to put me on page A19. So make sure you're on A19 now. So 20 degrees and then across the top, so from the numerator, and then 15 for the denominator because I flip-flopped them. And then I'm going to look for 0.025. So 0.025 is right in the middle there. It is going to be 2.76. Okay? Now 2.76 is not my critical value. 2.76 is my denominator here. I now need to actually go through and do that actual division, okay? And if I do 1 divided by 2.76, I'm going to get 0.3623, and that, folks, is my critical value that goes right here. So this value is 0.3623. Wow, this pen is really annoying today. All right, now I need to find the other tail. This one's a little bit easier because it is the right one. So it's just going to be f of this area, right? Because it's not going to be the 0.05 that was cut in half. So f of 0.025 with and I keep everything normal. My numerator degrees of freedom is 15 and my denominator is 20. So I'm going to go to 15 and 20 and that's on the exact same page. So 15 is the numerator, 20 is the denominator. I'm going to follow where those two things match. I'm going to go to 0.025, which gives me the number 2.57. And I don't put that over 1 or anything. 2.57 actually is my critical value that corresponds to here. So those are my two critical values if I'm doing my F distribution. If I got a test statistic, so my F score, that is in the middle of those two here, then that would be a no-go. If it was in either this shaded region, so it's greater than this, or this shaded region, meaning it's less than this, then my answer would be to reject the null and accept the alternative, okay, because it would be in the shaded region. Again, these are kind of tricky. I know that if you end up wanting more practice, we can do it during office hours. You also see one of those in your homework problems. All right, folks, so let's take a look at our first of two problems where we're going to be doing hypothesis testing standard deviations. Let's take a second and read this. So, an investor believes that Cisco Systems is a more volatile stock than GE. The volatility of a stock is measured by the standard deviation rate of return on the stock. So the standard deviation dictates whether something is volatile or not. The higher the standard deviation, the more volatile it is, if you think about it, right? You would want a stock to be very consistent, which would mean that it would have a small standard deviation. Everything would be clustered around the mean. Because volatile is kind of a negative thing, it would be something that is very inconsistent, and it would be with larger standard deviations. So the data in Table 4 represents the monthly rate of return between 1990 and 2014 for 10 randomly selected months and 14 randomly selected months for GE. So does this evidence suggest that Cisco Systems stock is more volatile than GE stock at a 0.05 level of significance? Before we do anything with this problem, we need to check three things. First thing, was the data collected randomly? And if you look back at the problem, it says random for both of them. Random here and random here, so we're good. Next, when we're dealing with standard deviations, you have to be dealing with an independent situation. Most of the times we are dealing with an independent situation. The only time that we really have to worry about that is if we're dealing with means, right? Means you have a different calculation if it's independent versus dependent. So here it's independent, it has to be independent all the time. And then the last piece is that it has to be normally distributed. Now, in the past, they'd say in the problem that it is normally distributed. You might run into that situation again. But if they give you raw data, you can actually check your normal plot if they don't tell you if it's normally distributed to kind of check that off. So it is random, it is independent. We're going to put our we are going to input our data into L1 and L2, and we'll just create a normal plot for both of those graphs, okay? So take a second, I'm going to hop over to my graphing calculator and input those values, and then we'll get started. So now that my values are all in, L1 is going to represent the Cisco Systems, L2 represents GE. I'm going to create my plots. So I'm going to go second y equals, which pulls up stat plot. I'm going to go to my first one. And now we do not need to do a box and whisker plot with standard deviations. We just need to look at the normal line, okay? We're going to look specifically right now at L1. So make sure that says L1. We're going to look at our x-axis as being where our data goes. And then to graph it, we're going to do zoom, and then we're going to go down to 9. And we can see, generally speaking, that looks pretty darn normal. Okay, and by normal, I mean it's linear, and linear would imply that it's normal. Now I'm going to look at my next plot. I can still use plot 1, that's fine. I'm going to go down to the normal plot. It's already highlighted, so I'm good to go there, but I'm going to change my data list to L2, so I'm going to press second 2. I want it to be on the X, everything else is good. So I'm going to zoom 9 that. And we can see that also looks pretty gosh darn linear, which means that it's probably normal. So we're good to go with that. We can put a check mark right there. So now that we've kind of done our quick check of those 3 important things before we really get going, now we're ready to start thinking about doing some hypothesis testing. So we're going to start by thinking about our null, and we're going to think about our alternative. So in this instance, we are comparing standard deviations. So we're going to be using our standard deviation symbol. The null is that there's no change. So we would say that our standard deviation from our first population is going to equal the standard deviation from our second population, right? There's no change in between the two. They are exactly the same. Our alternative, however, is that whatever's in our L1, okay, so that our Cisco systems, that standard deviation is more volatile, which would mean that it has to be bigger. The standard deviation would have to be bigger than what's going on in our second one, okay? So that's our alternative hypothesis, okay? I do also want to think right now, just because I know I'm going to have to do F-score stuff. Oops, I should not have drawn it like that, right? Because I'm dealing with a standard deviation, I am going to be dealing with a right tail because it's greater, okay? So I'm thinking, okay, it's going to be F with my alpha and then my numerator and then my denominator. Okay, this is my sample 1, so that's going to be my degrees of freedom for this for the numerator and my degrees of freedom for that for my second number. Okay, because it's right-tailed. This, whatever your first sample is, would be the top degrees of freedom. This is the second degrees of freedom that we're going to do. And our alpha value, they told us in the problem, oops, that's a horrible alpha, is 0.05. So now you're like, sweet, let's learn those keystrokes because we've been really fortunate. That's how a lot of this is done. We still will go over classical and we'll go over p-val. So for p-value, we are going to go to our stat menu. We're going to go to our test, which is always the way we go for hypothesis testing. And then we're going to go down to option D. And option D is 2, which hopefully you're like, yes, I know why it's 2. It's because it's 2 samples. Well, it actually says 2 samp, and then it's going to say F test because we're doing the F as our test statistic, and we're running a hypothesis test. So 2 samples, we're going to get our F score because we're dealing with standard deviations, and we're going to run a hypothesis test. So we will go stat, test, and all the way down to E, I guess it is on my calculator. I know earlier it was D on my other calculator, the one that I actually had in my hand. So it could be a different letter for you. Just make sure you're choosing the one that says 2 samp F test, okay? And you can see from here we have 2 options, just like we do if we're doing a t-test. You can do it from data or you can do it from stats. We have data plugged into L1 and L2 with a frequency of 1 on each. And then my alternative hypothesis here is that my standard deviation from 1 should be greater than 2. So I want to make sure this is the one that's highlighted. And then I'm going to calculate. And here I get that my test statistic, which happens to be an F score because I'm dealing with my F distribution, is 7.5193. Okay. And then my p-value is 6.9363. Okay, so 5193. So I'll put that over here because I'm going to use the F score on my classical. It was 7.5193. And over here, my p-value was, let's see, it looked like a 0.6, but I don't think it is 0.6. I think there was a little error next to it, so we'll have to go look at that, 0.69363. But let's go back to that for a second. Right here it says e to the -4. So remember, that's kind of like our scientific notation, right? There was an error. It's a -4, so we need to make this number smaller, okay? And this actually decimal point was right there if we actually look at it. Yep, 6.9. So because it had an e with a -4, that means I need to take this decimal point, which is where it was on the calculator, and move it forward 4 places, which will make this number smaller. So 1, 2, 3, 4. My p-value actually is 0.0007. Okay, and I just rounded that 6 up because we only need to go out 4 places. So that's pretty darn small. So if we want to just finish up our test with this, we could say that that has to be less than our level of significance, which is 0.05, and clearly that is, okay? That is true, that works. That means there is enough evidence we reject our null and accept the alternative. If we were to do classical method, again, it's not atrocious, folks. You just have to know how to do it, especially if it's a right tail, it's not bad. I'm going to sketch my graph. I'm going to find my f-score that corresponds to 0.05. And in my first, not list that I'm saying, in my first population, thank you, I have how many degrees of freedom again? Let's see. There are 6, 7, 8, 9, 10. So I have 9 degrees of freedom. And then here I have, let's see, 8, 9, 10, 11, 12, 13, 14. So 9 and 13 are my 2 degrees of freedom. So it's got to be 9 first because that's in my first sample, and then 13. So I'm going to go to the back of my book right now. I'm going to go to my A16 through A19, and I'm going to find my corresponding f-score that I'm going to use for my critical value, okay? So I'm looking for 9 across the top, and then I'm looking for 13 across the side. Now the dilemma is that there is no 13 across the side. There is a 12 and a 15. So what we are going to do is we're going to go to the closest number that is in the book, and the closest number here is 12. So we're going to treat this 13 not like 13. We're actually going to do the calculations or find the actual f value that corresponds to it being 12. Okay, so 9 across the top, 12 in the denominator. I'm going to go to 0.05, which is the second number. It is going to be 2.80. And that's an approximation because they didn't have the exact degrees of freedom. So 2.80. So if we think about it, if this number right here is 2.80, this 7.5 is definitely in the shaded region. We would say yes, it is. So yes, there's enough evidence to reject the null and accept the alternative. And then, like always, we write it just like we would normally write one of these. We would say something like, there is enough evidence at a 0.05 level of significance to say that the difference in deviation, okay, because we're looking at standard deviations here, that the difference in deviation is higher for Cisco than General Electric. You also could reword that a little differently. You could say there is enough evidence at a 0.05 level of significance to say that Cisco stock, because it has a higher standard deviation, is more volatile than GE stock. And that's what they were really asking us about, right? Volatile. So saying that Cisco stock is more volatile than GE stock would also answer that question. Let's do another one of these using another set of data. So this problem is very similar to section 11.3. It's all about our mice again, right? And looking at their red blood count or red blood cell mass in milliliters. Looking at both a group that went to space and a group that stayed kind of on Earth, and they both had the exact same conditions, okay? So the only thing that was different was that one is in space and one was on Earth. And then trying to determine what's going on there. So this now is different data than last time. It is not the average, it is the standard deviations, okay? So is the standard deviation of red blood cell mass in the flight animals different from the standard deviation of red blood cell mass in the control animals at a 0.05 level of significance? So we would have to check our 3 items here for standard deviation. We would first have to check, is it random? We would have to check, is it independent? And the 2 groups were chosen independently of each other. Okay. And then we would have to see if each of these is normal. They do not tell us if this is normal and this is normal, so we have to check for normality by adding everything into L1 and L2 and then doing our normal plot. We have to put things in L1 and L2 anyways, right? So we might as well do that right now. Let's put our flight in L1 and our control in L2. All right, so now that I have everything in L1 and L2, I'm ready to create my stat plot. So I'm going to go into second stat plot. In the last example, I already did the normal plot, so I know it's on, and I'm currently looking at L2. I'm going to have to do that graph anyway, so I'll just do it first. So we'll just zoom 9 that, and that is generally normal. It's not creating like a parabola, so that seems okay. And then I'm going to second stat plot. I'm going to go into it this time, and I'm going to change it from L2 to L1. And then I'm going to graph that one also. So zoom 9. And wow, that one's even more linear. Okay, so I'm feeling good about the possibility of both of those being normal. I'm not worried about having to not do my hypothesis test or getting a larger sample. Everything there seems good to go. Okay, so now I'm ready to write out my alternative and my null. So we'll start with our null, and then we'll do our alternative. My null is that there's no change. Okay, and again here we are looking at specifically standard deviation. They're telling us that. They're not telling us it's variance, so the standard deviation of my first should equal the standard deviation of my second. That would mean there's no change. I'm going to use flight as my first and control as my second. They want me to see if there is a, let's see, difference between the two. Okay, so that is going to be that they are not equal. So it would be that my first standard deviation is not equal to my second standard deviation. Okay, at a 0.05 level of significance. And this is a two-tailed test, which is not great when I'm dealing with an F distribution. That means it's going to be a lot of work. So I'm doing there and there when it comes to my classical method. So all three of those things are good to go. I have this. I'm ready to go onto my calculator again and do some work. Alrighty, so I'm going to go into stat, like always. I'm going to go over to test, like always. And then I'm going to go down to where I can see that it's going to be 2 samples. And then I'm doing an F test. So 2 sample F test is what I want. I'm going to use data from L1 and L2. I'm going to go down. My alternative hypothesis is that they are not equal. And then I'm going to calculate it up. So I end up getting these values. I get that my test statistic is 1.02. That's my F score. Okay, and I'd have to round it up to actually 1.204. And then I get that my p-value is 0.96657 or 0.9666. Okay, so we'll write those down in here. So if I'm going to do my classical, I'm going to need my test statistic, which is my F score of my null, which we said was going to be 1.024. If I'm doing my p-value test, I need my p-value. And the p-value here was 0.9666. So right now we could kind of come to our conclusion here. Is that less than our alpha? Heck no, it is not even close to 5%. So there's not enough evidence. We would say that they're the same. Okay, there's not enough evidence to reject the null, so we keep the null. So that means when we do our classical method here, when we find our 2 critical values, it's going to not fall. Our test statistic is not going to fall in the shaded area. So I'm going to draw my F distribution. I have a shaded area over here. I have a shaded area over here. each of these areas is half of what my alpha is, so it's going to be 0.025. This one is going to be 0.025. Let's start off with the easier one. I'm going to do the F-score of 0.025 with my L1 degrees of freedom, and I think each of these sample sizes was the same, 2, 4, 6, 8, 10, 12, 14. So this has 13 degrees of freedom, and this has 13 degrees of freedom. So 13 for my first, 13 for my second. Okay, and I'm going to go to my book right now. I'm going to go all the way to the back to page A16. And I'm going to look for my 13 and 13. So I notice 13 does not exist on the top. I already know 13 does not exist across the bottom, but 12 is the closest number. So I'm actually going to go to 12 and then 12. And then I'm going to look for 0.025, which gives me 3.28. Oops. So that means this value here is going to be 3.28. Now this, I already know, folks, from our previous example, that if I do f of 1 minus 0.025, I'm going to get 0.975. And there's no 0.975 in my book, okay? So instead of rewriting that, oops, I don't mean to put it with this. Instead of rewriting that, I'm just going to go for doing 1 over f of 0.025. And then it says that I would flip-flop these two, okay? But because they're both exactly the same, I mean, I could say I flip-flopped them. I'm definitely going to say I flip-flopped them because that's what you're supposed to do. So I'll find the F-score that corresponds to 0.025 with 13 in my numerator, 13 in the denominator, which actually, folks, is this number right here. It's the same exact thing. And that doesn't happen every time. That only happened because my degrees of freedom of both were exactly the same. Now, this F value, this critical value for that F score, is going to be 1 divided by 3.28, which is 0.3049. So 0.3049. Okay? So that means this value here, 0.3049. If I look at where is 1.0, it's in the non-shaded area. So is there enough evidence? No, there's not, because my test statistic is not in my shaded region. I could also say no because my p-value is not less than my alpha. Okay, so I would keep my null and reject my alternative in this instance. And what I would say for my kind of conclusion to that would be that there's not sufficient evidence at a 0.05 level of significance to say that the standard deviations of red blood cell mass is different in rats that went to space versus those that stayed home. Okay? So there's not sufficient evidence at a 0.05 level of significance to say that the standard deviation of red blood cell mass is different in rats that went to space versus the rats that stayed home. So that is it for chapter 11. That's a lot of stuff, okay? It's 4 totally different hypothesis tests. It has you looking at proportions. It has you looking at independent means, dependent means, and standard deviations. And a lot of it is just remembering what keystrokes go with what. So take your time on this homework. We'll cover the homework questions in office hours on Friday if you're interested. And then on Monday, I will put up the keys for the homework and offer to be available to you folks to answer questions about the homework before the quiz is due. The quiz is due when that homework would be due. It needs to be turned in as soon as possible because my plan is to post or review the answers to that quiz as part of our studying that I'm going to release on Thursday. So if you could get that quiz in sooner, it would be better. The deadline for it, without it being counted late or having to do the retake of Chapter 11 quiz, is going to be midnight on Wednesday. So make sure you have it taken care of midnight or before midnight next Wednesday. Again, on Monday, I will put up all the keys for all the homeworks and give you guys an opportunity to ask questions if you need to. Hopefully things with Chapter 11 went okay. If not, please be attending those office hours. Please reach out to me via email or Zoom or whatever you need to do to make sure that we can kind of solidify whatever we need to before you folks take the test the following week. So, thank you, folks. I will hopefully see you later. Bye.